So what I was saying was that TensorFlow allows us to create a data pipeline. For example, if I have 865 images and every image is 2 MB, which means it's going to create about 1.6 GB of data. And just like in machine learning algorithms, if your data is too big, all that data, and if you were not making a pipeline, what's going to happen? All that data is going to sit inside your RAM. And if you don't have a big enough RAM, your computer is going to crash. So that is where TensorFlow gives you a data pipeline option, which means you don't need to put all the data inside the RAM of your computer. You can convert it into batches, and it's going to only pull out certain number of images in a batch, process them, train them, and then put them back, and then pull the next batch. Which means at one given time, if my batch size is 32, let's say, for example, over here, I'm defining my batch size to be 32. That means in one single step, my RAM is only taking care of 32 of the 865 images. So this kind of like is an efficient way to use your RAM and increase the training time and not the training time, improve the training time and things like that. So when the data keep on getting bigger and bigger and bigger, these data pipelines are going to help you. Right now, let's say, yes, my RAM is too big. Right now, 12 GB, which means I can throw in all the data. I don't need to make a data pipeline, but I can throw in all the data in my RAM and my computer will not crash for now. But what if I'm in a company and they have terabytes of data? Then I don't have that big a RAM, which means then I have no other option just to use this data pipeline. So we need to learn how to kind of like use those pipelines. So how to do that is, it's pretty easy. You see, what I did is basically I made a data folder, and inside the data folder, I made 4 classes and the folder for 4 classes. And inside every folder, the images are there. The data pipeline generator in TensorFlow, what it does is basically it goes to that particular specific folder, and whatever the name of the folder is, it will assume that is the label of that image inside that folder, which means this particular image data set from directory thing, what it does is basically it goes to this data folder. Inside the data folder, there are 4 folders inside it. Every folder it will consider as one of the class. And then it will go to every single class inside it, and it's going to grab this image, and it's going to link this image to the folder name. And it's going to tell us that, oh, this image has a label dandelion. This image has a label roses. This image has a label sunflower, and so on. It's gonna do everything automatically. We don't have to do anything. What I did over here is I only decided or defined where my data is. Just told it that this is the folder containing all my data. Now it's gonna go into that folder and pull out all the information on its own. You don't have to do anything. Over here, I'm telling it that I need to divide it into validation set as well. So 20% would be validation set and 80% would be my training set. Then I'm labeling this particular subset as training set, which means this would be my training set. That means right now I'm taking that 80% of it. And then for validation, I'm going to do exactly the same thing. And I'm going to do validation, which means whatever I was not picking here, I would be picking here as validations. So it is exactly the same thing. What is this seed? Seed is basically random initialization, and we want to keep everything constant. That's why the random initialization seed number is same, 1, 2, 3, 1, 2, 3. This is a random number. You can pick any number you want, but as long as both the numbers here in training data set and validation data set are same, it should be fine. Then the next size is you need to define the size of the image. Size of the image is pretty crucial. We determined the size of the image somewhere where I think we did it later somewhere. Yes. So we did the size of the image somewhere here, 180 by 180. So did I do that? Yes, 180 by 180. You can see. So I determined it and then I put it here so that it doesn't change, because then these neural networks, these TensorFlow data pipelines, if the size of the input data is not right, it's going to keep on throwing the error. The adjusting the dimension is very crucial and very important. And sometimes this is the majority or bottleneck, you can say majority of the people get stuck here in understanding the dimensions when they need what dimension. Okay, so I created my training data set and I created my validation data set. Keep one thing in mind. These are not data set, which means if I print train_ds, it's not going to give me all the images, because this is just a TensorFlow data pipeline object, which means it doesn't have the images inside it. It's going to pull while training. If you want to pull all those things, you can use NumPy, iterator, or things like that. But right now, I'm not going to use it. So then what I can do is I printed out how many files I have, and out of those, how many I'm using for validation. And this many files, I'm using 692 for training. Now, class names, let's print out the class names. You can see it is automatically picking up the class names. I did not define anywhere. It is going inside and it is picking up the names of the folders automatically. Now let's visualize the data. So when I visualize the data randomly, some images with the labels, you can see these are tulips, 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 rose, dandelion, dandelion, tulips. So it's just random. So it is picking up randomly different images in a batch. Now, printing out these will help you, because if you would be asking me that why did I use 180 by 180, it's because I figured it out over here. This is telling me here that my image size is 180 by 180. What does number 3 means? 3 means it is a colored image. It has 3 channels, red, blue, and green. What this 32 means? This 32 means I'm picking out just 32 images per batch. So 32 is the batch size, 180 by 180 is the width and height of the image, and the number 3 is the 3 different colors, red, blue, and green. So technically, these are 4 dimensions over here. The first one is the batch size. The next 2 are the width and height of the image. And the third one is the channels, how many channels it has, red, blue, and green. For the gray image, this 3 would be 1. And you can see my target is just 32 things in batch. And this comma, nothing written here, which means it would be just it doesn't have any, you can say, dimensions, because my answer is just either it is a rose, it is a dandelion, sunflower, it is not an image. That's why it doesn't have any dimension. So over here, it is defined here. Next thing, what I'm doing is, so this is where caching and shuffling comes into play, and prefetching. Now, what happens is this data pipeline, it pulls 32 images and throw it into the model. Then model is going to do the back propagation and optimize the weights of that particular batch. While your processor is doing that, I can pull out another batch and pre-process it in the background, so that once my model has already optimized the training for first batch, I can right away, as soon as it is done, I can pull out the next batch, which is already ready for the processing part. So this prefetching and caching part is basically where I'm pulling out. So I'm keeping my pipeline active. Otherwise, what it's going to do is it will pull out one batch, do the processing, then throw it in the model, do the optimization, and then pull out the next one, and it will wait for the processing and then training. So I don't want to do that. If I want to make that process fast, what I can do is I can prefetch, which means while model is training one batch, the previous batch is already pre-processed and ready for the training. As soon as one batch is done, the other batch will come in and the next batch will pre-process. So prefetching makes the process a bit faster. So I kind of like define the prefetching over here so that I'm pulling out two batches. One is into the model and one is kind of like right now doing pre-processing. What is pre-processing? We'll talk about it. So pre-processing step, one of the step is standardizing the image. Means all those images are 256, means the numbers that we have in these images are in the range of 0 to 255, which means machine learning model, the bigger the number that you're going to throw in, the weights are going to be bigger and the computation power is going to be heavy. So the ideal thing is always normalize your data, keep it between 0 and 1. So that's where what I'm doing is there's a layer called rescaling layer. Just like the dense layer, convolutional layer, and pooling layer, there is a rescaling layer, which means you can add it inside your model. Over here, you can see this is my model, and I'm adding a rescaling layer. What it is doing is it is dividing every single value by 255, which means everything will be converted between 0 to 1 because the least value is 0, the highest value is 255. If everything is getting divided by 255, the biggest number is going to be 1, the smallest number is going to be 0, and everything will be in between. So now, deep learning models work really well if you have large enough data. If you don't have large enough data, that's where overfitting comes into play. Since I have only 865 images, and technically for training, I have 692 images, that is not enough data. How can I create more data? Now, if you have not seen, let me quickly show you. Okay, let me quickly show you what I'm talking about. Okay, so this is the image I created for my LinkedIn post. Let it open. Okay, you see the importance of data augmentation. This is a fun project I was doing. Exact same image, if you flip it vertically, it's going to throw in the garbage, which means it won't be able to recognize my face. Why is that? Because the convolutions and everything, they are sensitive to the variations in the space, which means if my face is in the middle of the picture, and in all the images, it is in the middle of the picture, and the testing set has my image on the right side of the screen, it will have hard time identifying it because it is remembering or memorizing the patterns that my image is in the middle. But if it is not in the middle, it's going to mess up. So data augmentation can take care of that. Data augmentation means it's kind of like cropping the data, rotating the data vertically upside down, horizontally left side right, or maybe shading it or cropping it or zooming it or things like that. So that is what we call data augmentation. So what I did over here is I just added few things just to introduce. I can add so many different things here. So over here, what I did is basically I did 3 different steps for data augmentation. I randomly flipped horizontally my image from left to right and right to left. I randomly flipped it, some of the images. Then I randomly rotated them 0.1 degrees on both sides. Okay. Then I randomly zoomed them into and out of them randomly, which means by applying these 3 augmentation techniques, all my images now have multiples of 3, which means 662, however many I had, 600 something, 692, about 700 times 3. Now I have 2100 images to train with, which means just applying 3 different transformations, I got 3 times the data. That means I can add more transformation, then I can increase these data, and I can add a blur. I can increase the brightness. I can decrease the brightness. I can increase the sharpness. I can decrease the sharpness. So many different things I can do. I can crop the image. So all those things are going to keep on increasing the number of images. So data augmentation is a very, very good way to kind of like produce more data. Now, so I did that. After that, what I did is, I think I'm showing you the wrong thing. So after that, you can see, so this is rescaling. My bad. I think I was showing you something transfer learning, but let's keep the basic. So first thing what I did is basically I normalized my data. Right now, there's no data augmentation because I want to show you what are the results without augmentation, what are the results with augmentation. So here, no augmentation is being applied. You can see the first layer is the convolutional layer. And here I'm doing the padding, same. And here you can see the activation function is ReLU. Then I'm applying the maximum polling 2D with the normal default features. And normal default feature is a 2x2 filter with stride length of 2. So it's going to do 2x2. Then another layer of convolutional, and then maximum polling. One thing to note about here, you see this number 16, 32, 64. Keep this in mind that you keep on increasing the number in powers of 2. You start with 16, the next one should be 32, the next one should be 64, the next one should be 128, next one should be 256, and you get the idea. Why is that? Let me show you. When you look over here, you can see that when I go from convolution to max polling, this 180 becomes 90. And then this 90 becomes 445. If I don't increase that number, then this would be pretty much different, and I would be losing a lot of information. So that's why I need to increase the number of filters every single time, or double the number of filters every single time, so that I can have as many features as I can. So that is the reason why we always start with the small number, then keep on increasing by in the power of 2. So this is 2 to the power 4, this is 2 to the power 5, this is 2 to the power 6. If I had another convolutional layer, I would be doing 2 to the power 7, 2 to the power 8, and so on. Then these are max polling 2D. If you want to change them to average polling, you can do that. Why these are 2D? You can see convolution is 2D because we are dealing with 2D images. If it was a video thing, then it would be, or time series thing, then it would be a 3D thing, because then you have a time dimension as well. So you can see that we have one module of convolution, we have second module of convolution, we have third module of convolution, then we have a flattened layer, and then we have a dense layer with activation ReLU, and then we have an output layer. And this output layer has a softmax activation function, which means this is exactly the same architecture I told you in terms of numbers. Now this is in terms of implementation. These are just these lines of code. That's it. Some of the lines are repetitive. So these 3 layers, you just copy paste them 3 times, just change this number. That's it. This 3 is telling you that the filter size is 3 by 3. And since the stride length is not defined, it is default, which is 1. Padding is defined here, same. If it was not defined, it would be default. It would not be same. Then you kind of like made your model. Now you have your model. What you can do is now you can compile. Compile requires 3 arguments. One is the optimizer. The back propagation is going to use a particular optimization function. Which optimization function it should use? Atom is a go-to one for majority of the problems as a standard one. You always start with Atom and then play with Atom or so many different others, RMS prop or SGD or so many different others. But always start with Atom. This is a good strategy because Atom is a universal one. Why Atom? Because there are so many different things happen, like vanishing gradient and those different things. If you don't know about it right now, don't worry about it. Just use Atom in the beginning. So then you need to define the loss function. So since in our scenario, we have multi-class, it is sparse categorical cross entropy. If it was a binary, I would have done binary cross entropy. So metric is what metric we are measuring. We are measuring the accuracy. It can be area under the curve, it can be ROC, it can be sensitivity, specificity, recall, or so many different things. But right now, I'm just using accuracy. Then look at the summary. This summary tells you the breakdown, how the dimensions of each individual layer changes. You can see the first one is this. Rescaling does not change the dimension, but convolution also does not do that, but max pooling reduce the size to half. Then convolution does not. If it was padding, it would have been reducing it, but then max pooling reduce it to half. Then it is same, then reduce it to half. And then we have a flattened layer. This number, you see this number, what this number is? You basically, how did you get this number? You multiply these three numbers and you're gonna get this. 22 times 22 times 64 is what you're gonna get. That means you have 22 rows, 22 columns, and 64 filters depth. And since I'm flattening it up, making one big column out of it, which means every single number should be the part of it, which means you can calculate it by 22 times 22 times 64 is going to give you this number. And then the next dense layer, you are giving 128 neurons as in, so this particular layer has 128 neurons, which are picking up these numbers. So then you have the final output layer 4, and number of parameters are basically calculated on every layer. And total number of parameters that we need to train while training the model is 3 million, 3.9 million technically, or 4 million, you can say on average. Now let's train it. When you train it, you can see I'm putting the training data set. I'm putting the validation data set for validation data so that I can look at the validation accuracy as well, and how many epochs I want it to run. For now, I'm just doing it 10. When I run it, you can see that this accuracy is the training accuracy. This is the validation accuracy. Look at these numbers. This one is keep on increasing. It reached 96%, but this one stayed at 80%. They started with very similar numbers, means you can see 0.68, 0.61, 0.73, 0.68, 0.74, 0.73. They were pretty close to each other. But then what happened? This accuracy kept on increasing, but this one did not kept on increasing. This is a clear sign and indication of overfitting the model, which means here our model is overfitting and it is maxing out at 0.82. You can say this is the maximum accuracy we are getting. But still there is a lot of overfitting here. Let's look at you can see until here it was pretty close, but now the difference between the validation accuracy and training accuracy is pretty big. And the losses are also pretty big, which means we don't want that. Once you see these kind of graph, these orange and blues getting separated, this is a clear sign of overfitting. Overfitting means the model has learned the data too well, but it is not doing really well on the unseen data, but it is doing really well on the seen data. So we don't want that. So that's where, so since our model was the basic one, let's see how we can improve. So when I do the testing and everything, you can see it is predicting, it is giving you these probabilities that the first label has a probability of 78%, which is dandelion. The second one has a probability of 9.9%. The third one has a probability of 0.6%. The fourth one has a probability of 11.1%. And this one is a dandelion, which means it is still predicting right, but the probability is pretty not that high. How can we improve it? Improving it is one way, I have already told you, data augmentation. And the other way is using already trained models. We call them pre-trained models. And so right now I don't have enough data, right? So what these machine learning scientists have done is they have gathered a lot of data. And they have made very big models, very complicated models, and they have trained them to identify to an accuracy of 99%, which means they have been trained on 1,000 different classes, on millions of data sets, on millions of images. Those models have been trained. So which means if I can get hand on that particular model and use it for extracting the features and add my own layers on top of it and apply it, I can get a good accuracy, right? I can improve the accuracy. And this particular thing is what we call transfer learning. So what you do is you basically grab a pre-trained model and add your own layers on top of it, modify it according to your specification, and use its learning to get your results or improve your results. That is what transfer learning is. So this particular notebook has exactly the same stuff what we did previously, exactly the same data, but here I'm adding two things: data augmentation, along with I'm adding, it's my VGG model. And along with that, I am pulling out a trained model. VGG16 is one of the pre-trained and the most less complicated model, you can say. There are less complicated than this. So 16 means it has 16 layers of convolution. So there is a VGG19 as well, which has 19 layers. Then there is AlexNet, there are ImageNet, there are MobileNet. There are so many different models out there. This one is a less complicated one, and if we print out the shape of it, we can take a look at it. For example, let's do that. So let's add VGG summary, right? You see this VGG model, it has 16 layers. The first one is the input. Then we have a convolution layer. It has two convolution layer, then max pooling. Then again two convolution, then max pooling. Then again three convolution, then max pooling. Now that's where the architecture, I told you the basic version where you have a module of one convolution, one pool, but people have tried several different architectures, two convolutions and a pool, three convolutions and a pool, and so on, which means you can try these things. But in the beginning, keep things simple, at least one convolution, one pool you should start with. But if it does not give you good results, then keep on changing things and see if it improves the results or not. And that's what these amazing people did. So you can see that it has so many, about 16 layers, and I am blocking its training. You can see vgg.trainable is equals to false, which means I am telling it that I want all the learned material from it. I don't want, when I add this in my model, I don't want my model to retrain it because it is already being, so they have already some learned stuff. I don't want them to forget it and rerun it. So that's why I'm blocking, or you can say restricting them to train again. So I want to use their trained version of it. So that's why I'm blocking their training. And over here, adding the model is pretty much same. I'm adding the data augmentation part. Then I'm adding the rescaling part, just like previously, normalization. And then I'm adding the convolution layers. Here, my convolution layers are the transfer learning part, VGG model. And then after that, my model is exactly the same as the previous one. The last layers, I'm not picking the last layers of VGG. I'm just adding my own layers. And when I run it, when I train it, based on everything same, you can see my results is going to improve. I had about 0.82 accuracy, and now my result increased to 0.89 or 89%. Technically, if you look at the highest number, it is 90%. That means I was able to improve my model with just small minor tweaks, nothing else. So with just few lines of code, I just improved my model. And this is what we call transfer learning, or you can also call it standing on the shoulders of the giants. Okay. If you look at the accuracy graph, these graphs are pretty good, close. They are still not ideal, but I can still tweak them and I can reduce it. Here, I added one more thing. Did you see this? This was not there previously. This dropout layer, what it does is basically, it drops out 20% of the neuron randomly during training. which means now my model is less complex and it reduces overfitting. So when I was not adding this dropout layer, my model was not that good. So what I did is basically I just added this dropout layer. By adding just one dropout layer, I improved my model comparatively because I was getting about 0.85. Now I have 90%, which means if I increase this number to 0.3 or 0.4 and try it again, maybe my model is gonna get better. So these are the things you keep on trying. When you make models, this is what you play with. Okay, and that's where your engineering brain comes into play, and that's where you're going to make your own architectures. These numbers, there is no hard and fast rule to get these numbers. Yes, we start with some basic ones, powers of 2, but you keep on changing them by improving. You need to improve your results. You keep on fluctuating them and changing them and see what happens, and based on that, just keep on changing if you want to improve your results. And finally, you compile the model, do that, and test it. You can see here we are testing. This one is not a good test. It is saying 50% it is dandelion, and 32% it is tulip. So it is still confused, which means for this particular image, it is not good. Let's see if it is doing good for another image. Maybe let's change the image. Let's take this one. I just copied these ones. So these are not part of the training image. They are just here. Let's see if this works for this one. Yep. So this one is saying 49%. It is this. 32% it is this. There's some mistake here. Okay. You see this model is still not accurate. 90% accuracy means it is still not 100%, which means it is still throwing an error. But let's maybe check here what kind of results we are getting here. %78 is this. It is saying it is dandelion. So it is mixing things up, which means we still need to optimize it to improve the results and things like that. And we have an image data set on TensorFlow. I can pull out that it has about 3,200 images. I can add those images with my images, and I can improve the data set, and I can do data augmentation, because right now I just did 3 different transformation of data. I can do 7 or 10 more. And then this way I will have so big data and my model is going to improve really well. Since this was a beginner workshop, I just wanted to keep things simple. And if anybody has any questions, feel free to ask. But that is what it is from my side for today. Anybody has any questions, please ask. Thank you so much.